Okay, so where are we on the overall scheme of things? All right. So we are actually at support vector machines. All right. So if you look at the overall algorithm map, right? We are at here. Okay, let me share my screen. Okay. All right, so you guys can see my screen here. So what we have, all right, we've been looking at algorithms, and we are looking at supervised algorithms, right? We are at classifications. We are just did logistic, and then now we are at SVM, right? Next week, we're going to go to naive Bayes. Okay. So looking at our course curriculum, so we are at support vector machines. So let's do a quick review and answer any questions you guys might have. How was the reading this week? Because the last week we had to do classification and logistic, but this week, since you already done the classification, should be pretty straightforward, I believe. Any questions, guys? Okay. So we are going to get started here. So let's look at some of the some Q&A, right, to make sure we are right. We all kind of understood about support vector machines. So what do you guys think is maximal margin classifier, right? Why do people say maximal margin when you talk about support vector machine? Yeah, go ahead and either speak up, guys, or we don't put it in the chat window. Either way is fine. Right, so kind of the way you have to picture this, right? From SVM is trying to divide the data, right? And if you look at that, right? So imagine I have 2 points like this, right? Like a blue points and orange points, and I ask you guys to draw a line that separates them. You can draw many lines, right? And which line are we going to pick? We are going to pick a line that has margins on both sides and kind of go through the middle, right? So so it has enough buffer zone on both ends, right? Because this way, if the data changes slightly, right, my line can still accommodate them. Because if I get too close to a point, to one side, if the data changes, right, then my line will not divide cleanly. So that's the idea. So what SVM tries to find is it tries to maximize the margins on both sides, right? Exactly, right? So that's why we call maximum margin classifier. Very good. What is slack? Slack, right? This is the SVM parameter. Has anybody looked into this one? Right, so slack is basically what we allow, how much we allow for misclassification, right? Because sometimes, you cannot do clean separation. So slack is basically, if you look at the diagram in one of the, and this is from the textbook, right? Right. And this is basically a soft margin classifier, because when you say soft, that means, there are some mispredictions. There are some data points on the other side, right? So you can see here, right? Like 11, this, right? This data point 11 is actually already supposed to be on this side, but it's on the other side of things, right? This data point 12, right? It's supposed to be on this side, but it's on this side, right? So this buffer zone, right, where we allow misclassifications is what's called slack. So if you make the slack bigger, right, you made it bigger, then you're allowing for more, more misclassifications, right? If you make it kind of smaller, then you're not allowing as many misclassifications, right, to occur. Anyway, so that's why this variable is called slack, right? And and it's literally called C, right? So you can control how much misclassification you can do, right? So if C means 0, meaning you have no buffer zone. That means no right? No violations allowed. Yep. So that's the idea. All right. So hopefully that made sense. Strengths and weaknesses of SVM. So can you guys tell me? Go ahead and type it in, please. I want to see what you guys think. What are some of the strengths and weaknesses of SVM? Right? Either you can speak up or you can type. Right? Right. SVM is very sensitive to data, right? So that can be a weakness because if your data changes during training phase, SVM algorithm can be sensitive. Yeah. Very good. Right. So in SVM, what Joe said was kind of called large data. It's true. So from SVM, there are two variants, right? One is linear SVM, which is kind of the, the line, right? Sort of the line, right? And this equation is pretty simple, right? So if you, and this linear equation is pretty fast. So it can scale large data. But if you do like these kernels, right? Have you, right? We looked at these kernel tricks. Did I ask you about kernel trick here? Oh, there we go, right? So kernel tricks are basically, like what if I have complex data? I cannot just draw a straight line. Then I have to add up these complex kernels, right? Here, here's like a circle, almost like a circle kernel. Here's like a polynomial one, right? And then when you choose these complex kernels, they, that's a lot of computation, and they may not scale to large scale data, right? So yeah, right. So depending on the kernel you guys choose, yeah, that's very good. Yeah. Right. Yeah. So what you said is true. Basically, SVM is very sensitive to tuning parameters, right? So you can spend some time tuning SVM, right? Because since it's very sensitive to the data, I mean, you can get good results out of SVM, but you have to kind of spend some time tuning it, right? So yeah, right, that's true. Anything else, guys? Anything else kind of, from SVM perspective, right? Strengths and weaknesses. So I don't know if you guys have seen this. I just want to kind of, go over this real quick, right? Doing the kernel trick. So imagine this data set, right? My blues and blue circles and red triangles. So there's no straight line to separate these guys, right? You can try to draw a line. You will not separate blue and red. So what SVM does, right? If you use a special kernel, they will project these things into a higher dimension. They will add, so here you are seeing, right? My original data was 2 dimensions. You can see here, right? And then what happened was SVM, this kernel adds a 3rd dimension. And what is the dimension? They're basically squaring one attribute, right? Feature 1 squared, right? And looks like this. So now the data is going to project it exactly into a hyperplane, yeah? So now you see this and you can say, okay, now I can separate the blues and the reds, right? Now this may seem like a little extreme, but it's very simple example. Imagine, you have like a flower vase, right? And in the flower vase, you have some marbles and some leaves, right? And I ask you guys to separate them, I ask you to separate both out. How do you separate the marbles and the leaves, right? You're kind of pouring, then imagine you're kind of pouring water into the vase, right? So what happens when as you pour the water, the marbles stay at the bottom, right? The leaves kind of start coming to the top, right? And then you sort of scoop out the leaves. That's kind of a crude example, but you guys get the idea, right? Because sometimes when you want to divide the data, if you can sort of project them into, extra dimension, you see the separation, right? And that's exactly what it's doing. And you can define, how many dimensions and what the formula and all this, right? And as you can see, this can get pretty complicated, right? I mean, you can see how many dimensions you want to add and what's the formula, all this. But SVM does allow for something like this. So what you have done here is, we have added, right? We added the 3rd dimension. And then when the 3rd dimension done, now I can sort of slice through, right? Because now all the red points are kind of floating to the top, right? Not this. Oh, the kernel is basically what's the shape of the dividing line. For example, right? The simplest form, SVM's kernel, let me go back here, right? It's a dividing line. It's called the boundary, the shape of the boundary, right? Meaning how am I going to divide these two classes? So here's a very straightforward line, right? But this line, and this is the original SVM implementation, but sometimes the line you just, cannot divide the data, right? And that's the example I was showing you guys, right here, right? Where was that? There you go, right? So if your data like this, blue and purple and blue again, there's no line you can draw to separate this data cleanly. So here they came up with a new shape, circle, or kind of circle. It's kind of like a circle, right? So these are called kernels. So kernels like an abstraction of your shape of SVM that allows you to separate the data. So more complex data. Yeah. So that's what you say kernel, right? So and that's what the example is walking you through, right? So there again, if you look at this data, there's no linear separation. You're going to draw a line and separate the data. So what we're doing now is just trying to separate the data. We are sort of projecting them out, and now I can find separation. But remember, my original data is two-dimensional, right? So I need to kind of bring it back to sort of two-dimension again, right? And so when I plot, make them flat, my boundary looks like this, right? Is that going to make sense, guys? Yeah. So now, what the shape looks like a nice kind of a parabolic shape, right? It's basically a polynomial or quadratic equation, right? And it's not a straight line, but as you can see, it clearly separates data cleanly. So anyway, SVM can do little things like this, right? So let me see if I guess so the animation. I think I put the link also in here. Yeah, right. So if you look at this animation right here, right? So take a look at this one here, and here, right? Here's some data. It's not a very high resolution, so you have to kind of look, right? But you see the red points and blue points, right, on a two-dimensional plane. But they're not separable. You can see, right? They kind of all intermingled there. So see what happens, right? What they're doing is they are sort of projecting them into a third dimension. See, like on a parabolic shape, right? Then what do you see? What happens, right? All the red points are kind of floating to the top. So imagine you're kind of pouring water into the flower vase, right? And all the blue marbles are staying at the bottom. All the red, let's say red leaves, right? They're kind of floating to the top, and then you can separate them, right? That's the idea here, exactly. And then you'll see like a separation plane coming in. There you go, right? So that's my plane. Pretty cool, right? So as you can imagine, there's a lot of advanced math at play, right? Projections and hyperplanes and all this stuff. But we, as soon as we understand the concept, this is done by the kernel themselves, right? We just simply choose the kernel and then configure the parameters, and and they will do the rest. But it's pretty cool, right? SVM can actually do this, right? So, all right. So that's that. Now, one of the things you guys learned is we need to normalize or scale inputs, remember? And that's part of SVM, right? So before you're using SVM, we need to scale or normalize data, because SVM will work better if your data is normalized, okay? And kernel trick is what I showed you guys. So basically rather than doing a simple linear, you can choose a kernel, and right, and depending on the kernel, they can do little tricks like this. And they can project the dimensions and all the cool stuff, right? So that's basically called kernel trick. Yeah, all right. Good, guys. So what else? Yeah, so strengths and weaknesses. Let's look at SVM real quick, right? And you guys have the slides already, so I'm just going to zip through this pretty quickly. Strengths. So linear version of SVM is pretty fast, right? You can learn pretty quickly. And also using the kernel trick, excuse me. And using the kernel trick, you can actually, solve, pretty complex problems, right? So SVM is very adaptable. Now, you can see weaknesses, sensitive to input data, right? When the input data changes, SVM changes. So you can say this is kind of high variance, right? That's a machine learning term, meaning when the data changes, my algorithm changes quite a bit, all right? And also, you can say it is sensitive to tuning parameters, because SVM is, right? You can tune a lot of SVM, a lot of the parameters, right? So you can spend some time tuning SVM, okay? And SVM does overfit. And now you guys know what overfit means, right? Meaning, just by the algorithm nature, it tends to overfit, meaning it does well on training data, not so well on testing data. So when you guys do SVM, I will watch out for overfitting, right? And also remember, when you do SVM, you need to scale data, right? And this is not a big deal, I mean, right? And this is just a couple of lines of code, but you just had to remember to do it. And then if you're using like this complex kernels, it may not scale to large data sets, right? Because remember, these kernels can get pretty complex, right? Complex mathematics. So the runtime, the training time will be longer. Yeah. So that's just comparing them side by side, right? Yeah. So question, yes, I would recommend you should convert this non-numeric data into numbers first, and that's true for pretty much all the algorithms, right? So I would recommend you guys do this, because especially when you want to test multiple algorithms side by side, because some algorithms can be a little forgiving. They can handle categorical data, but I would recommend converting them to numbers just in case. Yeah. Absolutely, yeah. So, all right, guys. So let's look at the labs, right? You guys are, all right, so Scikit-learn used the lab. So let me look at the lab here. So by the way, I was just looking at the submissions, right? So, right, only about 10 people submitted SVM solution. So I kind of want to make sure, you guys actually, right, putting in the work, right? Don't kind of let it slide, guys, right? Remember, this is for your benefit, right? So I really encourage you guys to submit the labs. So because we have what 20, 30 people in the Zoom, right, Zoom meeting. So I want you guys to right, participate. So just a little nudge. All right. So this week the solution is right. Here's a class submission folder, and I'm going to look at Richard your solution. Richard, are you here? Oh yeah. Yep. I see you. Thank you. That's yeah. I really liked your solution. So I made some few changes just to kind of explain a few things. That's it. But overall, your solution is perfect. All right. So I'm going to go through this one, guys. Right. So this is Richard's note. I just made some very minor changes to explain. Right. That's it. All right. So what is the homework? Right. Homework was basically using the exact same data. Right. Make blobs. Right. Use SVM. Use college admission data. Right. And also, as a bonus lab, you guys could find any data, right? And a lot of you chose income data because I just gave you the pointer. Now remember, this is the same data as before, and I kind of wanted to keep the data the same because we're not spending too much time messing with the data, right? So I want you guys to compare the algorithm side by side, yeah. So yeah, so if you're a little behind, again, don't worry. Just what I would recommend is if you're a little behind, like for example, right? So if you just joined us, I would recommend you sort of read up on classifications a little bit, right? And then you can skip logistic if you want, and then kind of come to SVM and kind of keep up with the class, and then you can go back and kind of catch up, right? Because otherwise, if you're sort of reading it in order, you're always going to be behind, right? Sort of just jump forward, kind of stay with the class, and then when you have time, kind of go back and fill in what's required. Yeah. So that's how this is designed, right? Because we want to make sure because it's designed for people who are busy, right? Because we have work, family, and everything else, right? So don't feel bad. All right. Stay with the class and then go back and do it as you have time. Yeah. No worries. All right, guys. So here's the solution. So let me go through this one real quick. So the first one, you guys know it's pretty straightforward, right? Make blobs. And how many samples, how many features, how many centers, right? Again, this, so we have 3 centers, right? And the cool thing about these make functions is they give you x and y right away. Right? And there we go, right? So for our x and y, so then, right, we are splitting x and y, right? The 20% for testing, right? And also random status set, so we get consistent ones. Okay, so that's the x and y split. Then using standard scalar. right, to scale the data, initializing SVM, and that's it, fit, X train, Y train. And I really like the liked your comments, right? So the code is very well commented and it's very easy to read. So really nicely done, Richard. Yeah, right. So so good work. Because I mean I know sometimes when you write code, we don't think we need the comments because we are kind of in the zone, right? And when you come back and look at the code a month later, it's still sometimes hard to remember why you did things, right? So I always recommend comment your code, even if it's obvious at the time. Definitely comment the code, so it'll help you a little later, and also help others who are reading your code, right? Exactly. So I see Vasili's question, like, what's the split? So yeah, right. So again, there's no like a formula. So it's, a lot of the time people do 80-20, and that's what's done here. You can do 70-30 as well, right? But also be careful not to take away too much data from training, right? Because remember, machine learning algorithms are only as good as the data they train on, right? So we kind of want to give them enough data, yeah, right? So if you detect the algorithm overfitting, you can definitely go back and say, oh yeah, let's take out some, increase this testing size and say, hey, you know what, I started with 0.2, maybe, let's do like, 70-30. Yeah, definitely worth trying. But also I will keep an eye on the accuracy as well, because you don't want to sacrifice the accuracy, right, to prevent overfitting. Yeah, so kind of a double-edged sword, right? Good. I guess for training, right, and then for testing, right, we do the prediction. And also it's a very nice job, kind of, right, variable naming, very important. So you can see, right, I definitely encourage you guys to stick to a variable naming convention. And this is what I use, and and it's very easy to use. And see how he said Y-pred, right? Predictions are Y predictions, right? So you have Y test as a test data, and then Y predictions is what the model predicted. And these are pretty standard naming convention. And like I said, and so when I'm reading this code and when I kind of see this, I know exactly what Y-pred means, right? I don't even have to go and look at the code, because I know exactly, right, kind of what he meant. So those are really good. And I highly recommend you guys kind of stick to those conventions, because I've seen like people doing like A, B, C, D, right? And it's a really huge pain to read the code, because you're like, every time you read like variable X, you got to go and say, okay, what is X really, right? So, right. So stick to the conventions. So it'll make your life a lot easier. All right, guys. So here's my confusion matrix. All right. Oh, okay. So it's coming up. And also I like the, I like the fact you had the plain confusion matrix, and all right, like this, and also the graph one. One thing I will add here, just to kind of make it a little easier to read. All right. Just want to say format as numbers, right? I think that's it. I think that'll, so see how it's doing the scientific notation here, right? It's kind of hard to read for us. So just, just say format numbers, and then, it's being so slow. And you see the actual, all right, actual digits. All right, there we go, right? You see the actual numbers, right? So, all right, good. And also a classification report you can print out, right? Another thing I want to add to this, okay, let me do this real quick. So as you're measuring, so okay, actually, as you're measuring the accuracy, right? So here's what I want to do. There we go, right? So what I want to do here, guys, is calculate the accuracy for both training accuracy, right? So model has a, do we have model function? Okay, it should be the same thing. my Colab is being very, very slow. Give me 1 second, okay? I'm going to, oh, there we go, okay. Let me just restart my runtime. Something is, okay, so much faster. Okay, good. So one thing you notice is like, right? So we are, like when you create the make blobs, you ask for 3 centers, right? Meaning, we have 3 clusters. So now the SVM is basically, right, separated in 3 clusters. So this is essentially multi-class classification, right? Your Y variable is 0, 1, or 2, right? If you say, right? So we print out Y, right? You'll see Y is, an array of 0, 1, 2. Yeah, there we go, right? So it's basically essentially a multi-class classifier, right? So even the original SVM was binary classifier, the recent ones, they can do multi-class classification. Yeah, so that's so because if you look at the Y, your Y is basically 0, 1, 2, right? So 3 classes. So think like A, B, C, right? 3 classes, and that's what SVM is classifying. And as long as they are encoded correctly, and here here they are just numbers, right? And SVM can handle them. Exactly. All right. So okay, let me do one more thing here, guys. Oh, okay, so here we go. Model score. So time by train. Okay. And did I get this one right? Train by train. Am I sure I got that all right? Because here's the X-train by test, by test. Oh, should be scaling. Okay, that's why. Okay. 1 second, guys. Let me quickly test this real quick. I was trying to show you guys something, but I'm gonna stuck on something else. Let's go. Let's see if this is the X test, Y test. That works. Sorry, I'm running into some. All right, I had to look at the shape. Okay, so I'll come back to this one. I don't want to spend your time just debugging this right now, right? So what I was trying to do is calculate the accuracy for both X and Y. Let me check something real quick here, and I want to come back to this one. Yeah, this should be it. Anyway, right? Because I want to sort of calculate the accuracy for both Y predictions. Yeah, right, confusion matrix. Okay, good. Sorry, yeah, okay, so let me sort of look at the confusion matrix real quick here, right? So remember, we have 3 class confusion matrix, right? So again, right, so, you can always very easily go and change here. You can say centers equal to 2, right? That means like, 2, so it's your standard binary, right? And then, right? So you look at the Y, right? Y is now 0, 1, okay? And your confusion matrix will reflect that, right? So and that's why the great thing about this make data function. You can experiment with different things, right? So let's stick with binary, right? Because that's simpler. And as you can see, it can do multi-class as well. When I say multi-class, more than binary, right? Not just A and B, but A, B, C, D, right? So on and so forth. Okay. So anyway, right? You can see the confusion matrix, and you can see the confusion matrix, right? It's doing pretty well on zeros, as you can see, right? And so right, it's correctly classified all zeros as zeros, right? 1 almost correct, right? Just missed 2. That's it, right? We'll remain confusion matrix. We want to see the diagonals to have the most numbers, right? And on a perfect matrix, we want everything else to be 0. But we don't get perfect, so right? So that's fine. Good. So I mean, yeah. So question was, how can you do 3 clusters? Remember, it's just just more dimensions, right? So kind of think about it in 3 dimensions. Like if it's like 2 clusters, right? So right, my line is straightforward, right? If I'm doing a 3 clusters, now my SVM line is more like a hyperplane, right? Kind of get a sort of project on 3 dimensions, right? And then say, because when we plot this data, right, this plot just does it in 2 dimensions. But imagine you had to sort of imagine your data in 3 dimensions. So rather than doing a straight line here for 2-dimensional data, for a 3-dimensional data, you have to imagine 3 dimensions. There's like imagine like a plane, right? Like a right, kind of like a if I'm holding like a like a plane like this, and there's some data here, right? Some data here, things like that. So right, so that's what it. Is that gonna make sense? So we are thinking like hyper dimensions, and SVM can handle that. Yeah. Right. Good, guys. Right. So hopefully that made sense. So this is synthetic data, right? So look at the college data, and again, this is the data you guys are pretty familiar with, right? So let me kind of look at this one real quick. Right, reading the data, right? Extracting X and Y. So X is basically GRE, GP, and rank, right? Y is admit column. So we know this by now, right? So and the reason we like this data is it's all numbers. It's all pretty simple to understand. Yeah. All right, that's it. Once you extract X and Y, it's basically then business as usual, right? X train, Y train, right? Scaling, SVC, right? All that. Okay. So let me see. Oh, I see. Okay, I think I made a mistake like this. Okay, so let me see if I can do this real quick. SVC score, extreme, train. This makes sense. There you go. Okay, so this is good. So I will do this. So this is training accuracy. All right. So I'm asking the SVS to score for training and testing data. I'm going to do the same thing for testing. Okay. So and then for testing data, we are going to score the data with test data, right? So X test, Y test. All right. Now we are going to print out right training accuracy is okay, and testing accuracy is this. Okay. All right. So let's try that here, guys. There we go, right? So we are doing a, how can I keep putting up this way? See, score. Okay. I should be getting a number. I'm not sure why this thing is SVC. It's printing out the model. Okay, 1 second. SVC, SV.fit, predict, score. Okay. So testing, I get about 79 or 80% accuracy. Am I doing a variable missing train accuracy? Oh, I'm sorry. Yes. Thank you. It's always the stupid stuff that trips you over. Right, there we go. I was looking for a number. Come on. There you go. Thank you, Chaitanya. All right, guys. So let's look at these 2 numbers, right? Remember we talked about the reason I'm doing this. So as you can see, right? So a score is a very handy model. You simply have to give the input and the output. Right? So it's like, right? I'm just like, you imagine you sort of did like a multiple choice questions. And then I'm saying, okay, these are the answers, right? This is the input and these are the answers. Now score, right? So it's pretty straightforward. And here I'm doing the training. And here I'm using the testing, right? So they're a match, X test, Y test. The reason I'm measuring this is like sometimes SVM tend to overfit. So it's always good to kind of measure the accuracy both on training and testing so you guys understand. And here, they're pretty much the same, right? So that's very good. And around like 80%, right? That's good. For example, right? So this is my, right? This is just to kind of verify overfitting, right? Right. So these are my things. So okay, right. So I kind of make it part of your notebook. Just always do both training and testing accuracy so you can spot overfitting right away. All right. And here's our usual confusion matrix and all the cool stuff, right? You can see, right? Again, same thing. Right. Just say format D, just so you know, get a little nicer output. That's it. There we go, right? So confusion matrix. So as you can see, right, this part is pretty much, I mean, all the accuracies, confusion matrix and all the stuff. This is pretty much boilerplate code, right? You could have copy pasted the same code from logistic regression to here to work. So what is the different? What is the only thing different is this guy. Right? So some people, right? Some people actually even to make it more generic, some people even say something like this, right? They will say something like algo equal SVM SVC, right? And then they say model equal, right? Algo.fit, xtrain, ytrain, right? The reason they sort of keep this name generic is, let's say they want to try a different algorithm. All right, let's say I want to try logistic regression, all right? That's it. You sort of substitute this, and then the code is exactly the same, right? So as you kind of go along, and you sort of develop your little techniques. You can say, okay, yeah, hey, I want to swap out the algorithm very easily, right? So you can you want to sort of start using more generic names, right? And because a lot of the classification algorithms, right, they're pretty, I mean, right, you see the code is pretty much like, all this stuff is the same, right? Only thing you're changing is basically your algorithm, yeah? So anyway, right, so you can sort of, right? So as you guys are kind of, learning more and more algorithm, you kind of want to make it easy on yourself so you can swap out the algorithm very easily. Yeah. All right, so this is very good, right? So good, really good work with all the comments, and really like the how clean the code is, right? So very very easy to read. So that's perfect. Okay. And finally, the bonus lab. This is the which I did the census data. So let's read the data here, right? So it's, as you can see, it's a pretty extensive data. Like you sort of see, education, mental status, right race, relationship, all the stuff, right? And the goal is basically to predict, given all this data, can you predict if this person is earning more than 50,000, right? So at the first glance, this may seem like a regression problem because you're trying to estimate the salary. No, you are not, right? You're only estimating if this person is doing more than 50 or under 50. That's it, right? So like yes or no, right? My question is this person earning more than 50,000? Yes or no, right? That's it. So it's actually a classification problem. So you can see, it has a lot of data, and some of the data you have to encode. Like for example, race, right? It's actually, right? You need to encode the date, race into numbers, right? So here's the right. So doing some basic cleanup, right? So we are doing like there's like some inane values and things like this, right? So you can do some basic cleanup here, right? And we are using label encoder to basically convert the data. Like for example, right, work class. What is work class here? Yeah, like where do you work? Are you in private sector? Are you state government, right? Federal government, whatever, right? So we are encoding those into a vector, excuse me, number, right? Occupation, same thing, right? What's your occupation, right? Right? Because this is going to be mostly text data, convert them to numbers, right? And also another thing, I sort of did was, this, you can see my comment, right? So if you look at this code. So another thing I did was I also encoded the label, right? Because if you look at the label I'm trying to predict, say I hate scrolling back and forth, right? You look at the salary, this is what we are trying to predict, right? Which is basically right now categorical, right? It says, less than 50,000 or greater than 50,000. I also want to convert this to labels, like 0 or 1, right? So I did that too, right? So I said salary indexed, right? Again, same thing. I use a label encode. I simply say transfer the name, right? And here's my encoded data. So you can sort of see here. Let me minimize this a little bit so you can see it better, right? So you can see, right? Okay, here's my encoded class, right? See word class numbers, right? So now word class is now encoded into numbers. Occupation, same thing, right? So now instead of adding clerical, let's say exec, whole numbers. Salary, right, is basically also indexed as 0 and 1, binary data, right? That's it. Good question. So should we do one-hot encoding, right? That's a great question. So here's the thing. Remember we talked about this when we just do simple encoding. Sometimes the algorithms might get confused, right? And they may treat this as like regular number, like when it's regular numbers, like something like this, right? For example, like age, right, where the actual sequence matters, right? So good, yeah. So here's the thing. A lot of the times, we can get by with just normal encoding. Some algorithms will get confused by normal encoding, and they will explicitly say you need to encode data in one-hot encoding. And then we will encode them into one-hot encoding, right? Now, so one-hot encoding is the safest option because, as you see, right, because when I look at this could be number, this could be right. But when you do one-hot encoding, it's a categorical variable encoded, right? That's the safest option. But just to sort of simplify our life, we can sort of start with this basic indexing, and if that works, we are good. Yeah. But some algorithms will explicitly say, yes, your inputs has to be one-hot encoded, right? And then we do it. Exactly. So here, we kind of took it in a little shortcut, and this seems to work okay, right? Yeah. So basically, when in doubt, use one-hot encoding. But most of the time, you can just do fine with just a simple encoding. Yeah, that's a great question. Yeah. Very good. All right, guys. So now my data is ready, right? So let's go ahead and grab X and Y, right? So here are my input columns, right? And the only thing I sort of changed this instead of the row salary, my Y is now salary indexed. Remember, the row salary is kind of right, 50K, under 50, right? It's like a string data or categorical data. Even though the algorithm did okay, because what they will do is like the scikit algorithms, they are pretty adaptable, right? They look at the data and they say, oh yeah, this is a binary data, and they will kind of adjust. But I recommend you guys actually encode it explicitly, because some algorithms will not do that, right? Just to kind of right, just to make sure we index them properly, right? So anyway, so it's always a good practice. Even though here you can just give the give the data and they will actually encode it internally. It's easy to it's important to encode manually, right? So you understand the process. Anyway, so that's the only change I did here, right? I basically said Y is index salary, right? Which is basically binary data. That's it. The rest, right? And here's I always say, right? Once you guys extract X and Y, that's it. Then it's basically business as usual. So that's why I kind of force you guys to kind of follow this format and like manipulate the data, do all the encodings, and do all the stuff, right? And basically come to a point you guys have X and Y. Then, right, it's like naturally you do the split, you do the scale, right? You do SVM, right? All that. So that's it. All right. So that's very good. So let me do the same thing. Let me do the print out the same training and testing data here. What was that? No. Okay. All right. So on the income data, right? Yeah, fade out confusion matrix. So if you look at the confusion matrix, you can sort of see here, right? Right. You can see the comparison, right? 0 is doing pretty well, right? Most of them can. 1, not so well, right? Because so it's basically misclassifying most of the ones as 0, right? So how can we fix that? Right? What do you guys think we should do to fix that? Not to improve the overall accuracy.
Hi, Suji. When I tried this, I actually play around other kernels, but it doesn't seem to have much improvement.
Right.
I also play with C, Gamma, and I think that I read those materials. They were saying
Yep.
that you can use the 0.1 as the starting point for Gamma. I tried those. I
Yep. Yep.
doesn't have much. I'm not so sure if because I'm not using correct features or something that I missed.
Right. Yeah. Yeah. No, that's good. I mean, and this is what I want you guys to get good at, right? Because, so the way I always do is like, okay, just go through and get a one baseline number. So now we have, right, and we can sort of because then we say, training testing, right? They're reasonably, reasonably close enough, right? There's no fitting. So we have a baseline number, right? Oh, should I get this one? Just I get the same number. 1 second. So yeah. Okay. Yeah. Let me do one more time. Okay. Right. So, so now you have a baseline number. Then we can now go back and then see what we can do. Right. So now I see some good options on the chat window. Right. So for example, yeah, can we do some hyperparameter tuning? Possibly, right? Because SPM has some parameters we can tweak, right? So we can play with those, right? Or we can, like Vasilios was saying, we can add features because if you look at this, the data has tons of features, right? We only added how many? Like 4 or 5, right? So maybe we want to even include other features as well, right? Exactly, and see, if they make a difference. Because remember, your best bang for the buck is going to come from feature manipulation, right? It's very rarely, let's say your algorithm gives you 70% accuracy. It's very rarely you're going to go from 70% to 90% just by tweaking the parameters, right? Tweaking the parameters will give you maybe like, maybe like a single digit improvement, like maybe like a 5%, right? Where your biggest win is going to come from is basically, incorporating the data, right? So that's why understanding the data is very critical, right? We want to make sure we get it and we want to make sure we include the most important ones, right? For example, I will definitely, let's see, we have race. I will definitely include, race, right? And sex, because we know, right? I mean, as unfair as it is, right? We know there's a discrimination, along those lines. So I will definitely include, definitely encode these guys, into right, to encoding and then include race and sex. Yeah, that's very important. They'll actually, I don't know if anybody else did this with the race and sex included, and I don't know if you guys had a better accuracy than 80%, right? So again, again, the thing is there's no right or wrong answer here, guys, right? My goal here is to show you guys the methodology. So you can pretty much go tackle, any data. So this is good. I really like, so, I really like how you started with sort of, right? Some of the, right? Because we don't want to spend too much time messing with the data. So we started with some basic data. Okay, now we have a number. Now we go back and iterate over this and then see if we can do better. Right, that's it, right? And also just to be thinking, right? I mean, 80% accuracy is not bad at all, right? Sure, right? I mean, we are like, so it's not like, it's not like we are at the 60% dial, right? We are at 80%, that's pretty good. Then we like to get as more. Good, guys, right? So again, hopefully, like, and here's my hope, right? I mean, now we have done 2 classification algorithms. One is logistic and this is SVM, right? We'll do the next one, naive based next. So you should be sort of getting the hang of the workflow, right? Okay, given the data, okay, what am I doing? Step 1, step 2, step 3, how we are doing this, right? And the reason I'm sort of forcing you to kind of go through this sort of, kind of a systematic way is it kind of gives you a little order, right? Okay, first I read the data. Then we do some basic data exploration, right? And then we do some cleanup of the data, right? And another thing I will, and this is just the, just the only feedback I will give you here is, right? And you're doing this already, right? When you get the data and doing some cleanup, also doing some, spend some time with some, use the describe function, right? To kind of explore the data, right? Just so you have an understanding of what the data is laid out. Because remember, describe function will actually give you, right, column by column breakdown. So use that, right? And it'll do the hard work for you, right? So can do that and kind of So you'll say, do we have any outliers? Do we have any invalid values? Things like that, right? And I know you already have done something here, right? Yeah, so very good. But yeah, overall, very good notebook, very well done. So Wesley, do you want to explain? You want to tell us about the library? Please go ahead. Yeah, if you can, go ahead.
I don't know if you can hear me.
Yes, go ahead.
I just seen it somewhere. Somebody was
a little louder, please. You're coming in very, very weak. Maybe a little louder.
Sorry, can you hear me better?
It's okay. Anyway, go ahead. Yeah, that's fine.
I was watching somebody explaining this library, and somehow I found it contains a lot of ways to see your data, visually and mathematically.
Okay.
And you can also, if you find something really nice you enjoy, you can tell this library to give you the source code, how you present things.
Okay.
So for learning about exploring the data, I think it's a very nice starting point.
Interesting. Okay, yeah, looks pretty good actually. Yeah.
If you try, for example, to say, show me the histogram of this feature, you can then get, say, show me the code of this,
interesting.
histogram.
Okay, gotcha. Oh, cool. Okay, I like that. Yeah.
Try click one, for example.
Yeah.
Try to get an example you like.
Okay, so like highlight missing maybe. Oh, interesting. Oh, cool. Very nice actually. Yeah.
Yes, and you can say, give me the code for this. Give me the source code for that.
Where do I get that?
Usually, if you get, say, histograms.
You see, sorry, okay, tell me this. So charts, histogram, is that what you're saying?
Yeah, you see the top right corner.
Oh, okay, I see. Okay, right, got it, okay.
Yeah.
Code export. Sorry guys, I'm a little, where am I? Code export.
Top right.
Back to data, that's what I see.
Back to data, sorry. If you put it into your Jupyter,
Oh, okay. All right, got you. No, that's pretty good. I mean, yeah, this looks pretty neat, guys. I mean, yeah, again, I'm just exploring. So this is pretty good, guys. So see, so we all, website. Let me go back here. Let me put the link for you guys here. Right, this is nice. Yeah. This is very good. Yeah. So good, really good find.
It takes some time, but you will get a lot of things out of it.
Yeah. So especially if we are doing a lot of, right? Let me see. Right. So yeah, anyway, so okay, now I don't want to go through this now. So you guys get the idea. Yeah, this looks pretty impressive. So really great find, Wesley. Thank you for sharing with this. I will spend some time kind of playing around with this too. But yeah, this is pretty neat, right? See how they do it. Oh, wow. Okay, cool. Interactive too. That was very nice. Okay. Yeah. Very cool. NATO. Yep. Really good find.
Try to see somewhere on the screen. Usually it says, "Get the code for this."
Copy link, copy export, code export. There we go. Right. I think this is what you mean. Yeah.
Sorry.
Yeah. Gotcha. Oh, there we go. Cool deal. Oh, nice. Yeah. This is actually this is something new. This I haven't seen before. The code export. That is very nice. Right. Yeah. Perfect. There we go. So now they write Python code for you. That's pretty awesome. Yeah. This is very good, guys. Yes, I really like this. And this is the and this is the right. I mean, this is a classic great example of kind of shared learning, right? I mean, so I wasn't aware of this, so now you showed me like a pretty nice nice package. Yeah, absolutely. Yeah. Detail. Nice. Cool. Good, guys. So again, seems like a very well thought out library. I can just kind of, as I'm sort of scanning through, I can tell, right? Yeah. So definitely worth knowing. So thank you so much, Vasilios. Yeah, very good. Good, guys. What else here? Yeah, this is very good. I'll actually put this one in our links, right? Just so you know it doesn't get lost in the chat window here. Because I would say I'll do it now, right now, because sometimes I'll just slip through. Okay. Sorry, I always misspell your name. So. Yeah. All right. So right, so it's in a welcome page. So right, all the right. I'll just add these as we go along. Right. So this way it doesn't get lost. Perfect. Thank you so much. This is really great. Yeah. Cool. Good. All right, guys. So let's get back here. Yeah. So like exploration, like I said, really great notebook. Very easy to read code. Very concise code. So that's right. I really liked it. So now here's the thing. Because right, I don't want everybody kind of doing this census data, right? I just gave it to you guys as an example because that's kind of it's only easy data. Please find your own data, right? I'm hoping you guys have your own data set, right, from UCI or or any place, right? I mean, there are right. If you look at our data, right, the data section right here, right? So I've given you guys a lot of repositories where they're going to give you give data. Pretty much anywhere from grab some data, some interesting data, right? And then once you guys have done the cleanup, that's it, right? You're done the hard part. Then sort of keep that and use the data over and over again with different algorithms. So you'll get a sense of how the algorithms work. Yeah.
So, Professor Suji.
Yeah, go ahead, please.
Hi. One of the things that I think that's what I try not to do, and it's like the only easy set that I ever was able to do is like a standard one, which is like two boilerplate, like iris data set, like that's two boilerplate, like that's popular, everyone uses. Some of the things that I began to notice is when I try to use the other data set analysis on the UCI repository, it did not allow for me to check for precision and accuracy. I kept getting an error saying that from the way that the data was structured, that what happened was, although it's multi-class, the other things the other labels were binary, and that it couldn't go and proceed with what I wanted it to do.
Right. Yeah. And I sympathize with you. With your thing is like finding good quality data that is also easy enough to kind of process is always a challenge, right? Because sometimes you go to let me show you sometimes I go to UCI, right? And then I look at say classification, right? And some of this data I have no idea what they mean. You know what I mean? Like it's very hard to kind of do machine learning on a data you don't really understand. So that's why I have a few favorites I can do this, right? Let's see if they still have this diabetes, right? So this is a reasonably good data set. It's called diabetes data set, right? And if you look at this, right, they kind of have it's a reasonably well-behaved data set, data folder. Anyway, you can download this and see this, right? Yeah. So that's why I kind of want you guys to kind of do some, right? And the thing is the reason I don't want to mention this, because if I mention it, right, everyone will just do that, right? So that's why I wanted to kind of have you guys do some research. But I completely understand what you're getting at. Finding good data that's not stuff like iris, right? And don't do iris, right? Because iris is just so overused. You want to pick a data that is a little different, right? So yeah. So I very well understand what I'm asking you guys to do. It's not trivial, right? Sometimes you get sometimes you sort of randomly click on data, and then you luck out and then say, oh cool, this is cool. I understand this and I'm going to use this. But yeah,
and
that's part of the challenge.
Yes, yes, yeah, that's part of the challenge. The thing is I also, when you deal with missing data, sometimes like sometimes it's going to be a hard decision. Like it's going to mess up your analysis. Like like some of them you can't like impute them. You can't eliminate the columns. I mean, you could choose what to analyze in the feature columns, but the thing is, it's like you can't. The thing is, because it's scientific or technical data, it could be a hard decision if you're going to try to handle the missing data.
Yeah.
It's not a good idea.
Like for example, like for example, this 2.4 right? I mean, like stuff like this, like I don't kind of want, right? I mean, sometimes it's very hard to kind of decode what the data really means, right? So right, so so that's one of, yeah. So I fully sympathize, and that's why I kind of wanted to give it to you guys early on, so you can kind of keep searching, and then if find the one that works for you guys, right? So I understand. So you can always use sort of the census data as a fallback, right? If it comes to that, but definitely, and also let's see, see in our data sets. If you download our data sets, let me bring this up, because the data set we have was, we actually curated the data sets for us, like what works here. Let's see. So census income is the data we just talked about. So college admission you guys have done, right? Okay, so we have diabetes data right here. Something called direct marketing. This is a reasonably okay data, I think. Let's see, yeah. So look at this direct marketing data. I think it's from UCI, right? You can sort of, you can look at this, right? Something like this, right? Your bank marketing set, right? Yeah. Yeah, so I understand. So again, and this is part of a, treat it like a part of a little challenge, right? Because finding good data to learn from. Yeah. So, and that's why I kind of wanted you guys to kind of, find your own, right? And so I see Vasily said, oh, the breast cancer data set is pretty good, right? Yeah, that's a good data set. You can use this. But you sort of understand, my hesitation of like not telling you guys, pick this, because, then everybody will have the same data set. I kind of want to see some variety, right? Yeah. So yeah, so, don't be discouraged. It's not an easy thing. I completely understand. So, just gonna, look around a bit. Sometimes you just do some Googling. You can say, classification data set, right? And you'll see some blogs and kind of look through those. Say, oh yeah, maybe I'll look at this, right? So yeah. So housing data, real estate data, you can definitely choose, but I don't, because most of the housing data will tend to be regression data. Regression as in, predicting house prices, things like that, right? I don't know I don't know if there's a data, housing data that for classification. There might be one, right? Again, I'm not saying there isn't. I haven't seen one personally, right? Yeah. So, so do some search in UCI. Right, and the reason I like in UCI is, they kind of have you classified already. Like, you can say, okay, I want regression data, right? These are the data sets. I want classification data sets, right? But again, it's not easy picking one up, right? Because sometimes it could be, right, right, just too complex or just too cryptic data sets. So, good. All right, guys. So kind of like I said, treat this as like a sort of, like a little personal challenge and trying to find your own data. Yep. And usually what I do is once I find the data and I spend some time cleaning up, then once I cleaned up the data, I save the clean data, right? Because, I don't want to go through the same thing on every notebook, right? So let's say I loaded some data, I did some cleaning up, and now I have like reasonably clean data. I save that as a CSV or something, right? Then from that point on, I simply load the data. Load the clean data. So this way I'm not spending, cleaning up, on every notebook, right? So, yeah.
I don't think that, I'm kind of unsure, like saying that I don't want to spend, I kind of don't relish the idea of trying to convert everything to a CSV file. I mean, that's why I like that, like archive, like put in those single quotes archive link. But the thing is, I sort of like, I mean, sometimes I can do like the .data files, but I tended to worry if I use like the .rar files or anything else or whatever other extensions. I tend to worry about it.
True. Yeah, that's a good point. Right. I mean, yeah. So I mean, yeah, I take that point. Not everything's going to be CSV file, right? But let's say you found like a JSON file or some other different format, right? At the end of the day, right, you are going to basically convert them to a data frame, right? Basically, so so whatever the data format is, right? You're going to read this, pandas.read.something, right? You're going to bring it in as a data frame first. Mm-hmm. And a lot of the time, pandas will handle the conversion. But let's say you have some obscure formats, some fixed length format or something, right? When you read it in, but once the data is in memory, you get a data frame. Is that going to make sense, right?
Yes.
Yeah. So, okay. So here's, I will give you both sides on this one. If you look at all the notebooks, right? So let's look at this, the census income data, right? Where we are spending most of the time is when, like shaping the data, right? Reading the data, cleaning it up, right? Converting them to numbers and all this stuff, right? And this is where you're going to spend most of your time, okay? Because the actual algorithm, you can see, right? It's just maybe 10 lines of code, like, with including, split and everything, right? And this is pretty boilerplate. You can pretty much copy this code into a new notebook and you can be up and running. Now, having said this, so the algorithm part is easy. Right? The data part is a little challenging. But at the same time, unless you really have a need, don't spend a lot of time trying to understand obscure data. You know what I'm saying? Right? Because, that's not a very, how do you say? It's not going to, it's not, your ROI, your return of investment, right? Basically, it's not very high in understanding obscure data sets. Do you get what I'm trying to say? Yeah.
Yeah.
So you kind of want to pick a data set that's real enough, right? It's not like a built-in things like iris, because that's just too simple, right? And then, right, you want to pick something real world-ish, but at the same time, you don't want to spend just too much time just digging through and cleaning up, and at the end you're like exhausted. So, and that'll definitely put you off, right? So don't do that either, right? Again, my personal opinion. So you kind of want to find a data, and that's why you can sort of look through our data set, because the ones we have, right? If you look at the, our elephant scale data set, right? These are curated. I mean, you can download this, right? And if you once down and look through this, I mean, I wish we had sort of had it classified, but we haven't. We actually just put them all in like one, right? Like, for example, the heart attack prediction, right? It basically tells you, given a bunch of symptoms, is this person prone to heart attack, right? 0 or 1, like binary classification. So you can sort of see these. So these are reasonably clean data, but still real world data. Yeah. So yeah, so don't go looking for like a really complex data, because then, what you're getting at is basically you're getting a PhD in data cleansing, right? It's not a bad skill to have, but, given them a limited time, right? Let's spend it kind of wisely. Yeah. Yeah. That's all.
Okay.
Yeah. Yeah. Right. So yeah. So and that's why I sort of given it to you guys as a task, because there are tons of things. I mean, sometimes when I read a blog of somebody's, like, Medium or data science or something, they will say, I'm going to use the data. Then I say, oh, this looks like interesting data. So let's go look at it, right? And then if I like this, I will usually kind of add it to our own data set, right? Because they're like, oh, that's a good, clean data that, we can use. Yeah. Yeah. So anyhow, right. So hopefully, I gave you something to think about. So because people think, real data is messy, right? We all get that. But thing is, once you know the basic processing, you don't need to go, you don't need to really go deep into that, because it just, just because at the end of the day, it's just part of your like workflow, right? Just want to understand, okay, yeah, this is how we clean up data. This is how sort of, fill in missing values. And you guys have already done this, a few times. So I think you're in pretty good shape there. Yeah. So, all right, guys. So let's see what else we are doing here. Okay, good. So here's a simple equation I want you guys to think about, right? When you're trying to spend some time on, on a task, I always look at it and say, what is my return of investment on this task, right? And not every task is going to have a high return of investment. We call them ROI, right? Because some of them you just have to do, and you just you just have to get through it. You're like, okay, yeah, I hate it, but I have to get through it. Right? Some of them, when you spend some time, you learn, you learn quite a bit, and they're like, oh wow, that's a pretty good ROI. So always think about this when you're learning something, doing something in task, and say, hey, do I really want to spend time on this? Right? I mean, is it worthwhile? Is it going, is there a good ROI for me on this? And only you can answer that, right? Because only you know how much time you have, only you know what your life goals are, right? So if you can answer this and you say, yes, this is worthwhile for me, I want to spend some time doing this, then by all means do it. Yeah. So ask yourself that single question, like, is this worth spending time on? So that should give you a pretty good, at least, give you a pretty good guidance. All right, guys. So let's, any other questions on this one? So where are we, right? Kind of, big picture, right? I want to make sure we all, so here's the thing you guys are seeing now, right? Now the labs are going, now you can see that, now that we have done the hard work of understanding the basics. So things like confusion matrix, right? All this. Now, when you look at the, when I say, this is the first classification lab we did. So, it was a bit of a struggle, right? We kind of want to understand a lot of these concepts. Okay, how do we do this? And then now we are doing SVM. You see, it's okay, yeah, so I get it. It's pretty much the same, just a different algorithm, right? Next, we are going to do naive Bayes, right? You do the same thing, right? So anyway, so the idea is like, as you kind of learn the fundamentals, then, our learning will accelerate very quickly, right? So you can look at anybody's code, right? You kind of go and say, okay, I'm looking at this code. And that's why I'm sharing the code, right? The class submission with you guys. You should be at a place you can sort of look at somebody's code and say, aha, I see what he's doing, right? In like a quick glance, right? For example, like, here, here there's, I say, oh, I know what's going on here, right? Okay, yes, train to split, okay, great. He's doing 20% split, right? Oh yeah, we are scaling. See what I mean? You should be able to like just quickly glance and quickly get an idea of what's going on. Where you spend more time is saying, okay, how may okay, what are the attributes I'm choosing? What am I encoding, right? Right. Those are the things going to be different for each notebook. Yeah. Good guys. So hopefully I'm hoping you guys are kind of at this place you're kind of right. Things make sense, right? You can look at other people's notebook and then quickly see what they've done differently. Right? Sometime when I look at some of these code. I say, oh, cool. That's a neat trick, right? I should learn that, so I should save this, right? So, for example, let's say if you guys liked, how, Richard used heat map for confusion matrix, right? Which I really like, right? And I say, oh, cool. This is nice, right? So, kind of just copy paste, save this in your own library. So this way you can keep building up your library, right? So, good guys. So that's it. So, Richard, thank you. Great notebook. Anything else, guys? Any other questions? Again, the links are here in our usual place, right? Into our guide. So class submissions and Richard's notebook. Yeah. So that's that. I think that's pretty good. Next week content, I need to actually update this. We are going to look at naive Bayes. So let's talk some big picture here, guys. Right. What I want to do is once we done naive Bayes, I'm thinking of, okay, there we go, right? So we are kind of here, right? So we'll do naive Bayes and KNN. These are, pretty straightforward algorithms. And once we are done this, we'll take a break. And what I want to do is, during the break week, maybe 1 or 2 weeks, depending on, what your preference is. And this is why I'm kind of pushing you to go find your own data set, because then what I want you guys to do is select a classification data set and use all 4 algorithms, right, on the same data set, and then see which algorithm gives you better results. Right, kind of like more like a stepping back, and kind of now we are sort of, you're stepping back a little bit and evaluating. Okay, I know these 4 classification algorithms. Okay, which one's great? Which one is really giving me good results, right? So that's what's coming up next. So I want to sort of quickly knock off these algorithm naive Bayes and KNN, right? And then we're going to go to we'll take a break and do like a little kind of a project. Does that make sense, guys? Because by the time you will be pretty comfortable know the algorithms, and you should be able to evaluate which algorithm works. Because sometimes like for example depending on your data size, on your data, some people might find SVM gives them better result. Some people might find logistics gives them better result, right? It's completely dependent on your data, but only you can evaluate, right? So we'll get to that. So is that gonna make sense, guys? So we'll probably take a break in about 2 weeks. That sounds good? Yep, and also it'll give you a chance to catch up. And so, and with that, we'll sort of wrap up classifications, and then we'll go into decision trees. Yeah. Does that make sense? Yeah. Good. So that's it, guys. So that's it for today. Any other questions? Oh, so what are some of the classification metrics? Question was, we've been using confusion matrix, right? So for classification, confusion matrix is a pretty good place to start, because remember, from the confusion matrix, did I close or not yet? Okay, so from the confusion matrix, right, you can calculate a lot of other metrics, right? So remember, and this is where the classification report function is there for, right? It will actually calculate a lot of other metrics like precision, recall, and all this, right? I would recommend you guys spend some time reading up on these, okay? Because these are, like I said, as you can go more advanced level machine learning, we will grow, we'll go beyond accuracy. Because right now I'm just using accuracy because it's simple to understand and just simple metric, and we all get it, right? As you get more and more advanced, right, you kind of want to maybe consider these, right? For example, think about this data set. Imagine you're doing a credit card fraud data set, right? So when a bank is let's say I'm doing credit card fraud, right? And so for example, let's say I have 1,000 transactions I have. Most likely out of 1,000, I would say 980 are good transaction and 20 are fraud. So this is a heavily skewed data set, right? And this is what you would expect from your bank, right? You don't want to do business with a bank where it's like fraud is 50%. So that's another problem. So a lot of the time, these cases, like things like this, will be very highly skewed data. Now, for these data sets, relying on accuracy is not good enough, because that'll give you a false picture. So then you have to kind of go back and look at these guys, all right? So and it's like we're kind of more going a little bit more advanced territory. So imagine you have a data set like this, and you sort of do your classification and get your confusion matrix. How do you know your model is working well, right? So yeah, so read a little bit about this, and also I will give you some links for some advanced metrics as well next week, right? When I'll update those. Yeah, but confusion matrix will get you pretty far, right? Because so don't just think confusion matrix just for accuracy, right? Look at the classification report and do some reading on these as well, right? So good question. What else, guys? So guys, let me open up for any questions, comments. How's it going? Is the work too much, too little? How are you guys finding this?
Can you please again show the outline that you showed, the classification and what you're going to do next week again? I'm sorry.
Oh, sure. Yeah. So right now, we just did SPM, right? So next week, next 2 weeks, I want to focus on naive and KNNs, right? So this way, we have a few classification algorithms under our belt. And there are, just to be, there are a lot of classification algorithms. These are some of the most popular ones. And I always say, right, as you can see, using the algorithm is the easy part, right? As you I keep saying, right, you usually get sick of me hearing say this, right? Right? Like I said, algorithm is just this. So let's say, you find a new shiny algorithm, you can simply, replace this with a new algorithm, and everything will be the same. Yeah. So right. So that's why what I'm sort of trying to build for you guys is sort of the methodology, right? So people ask me, I heard about this hot new algorithm. Are we going to cover this, right? Probably not, because remember, once you know some of the basic algorithms, you probably know, how to use the rest of the algorithms, right? So I'm sure, the new algorithm might have some more, tweaking parameters and all this, but once you guys understand the workflow, you will know how to use it. So don't stress out, right? Oh, I just read this blog about this new algorithm. Are we going to cover this? Right? That's fine, because just understand the fundamentals, and you see the scikit, and that's why scikit is really great, because the API, as you can see, right, things like this, right? all the algorithms support the same API. Right? So you can easily replace the algorithms with the new shiny algorithm, and just only have to change a few lines of code. Right, so got it? Yeah. Just remember, there's always going to be new algorithms coming online, right? So, that's that's kind of an arms race, right? It's like, you just cannot just learn all of them. So learn the fundamentals, and then you can pretty much adapt any algorithm that you want to use. Right. So feature selection extraction, exactly right. Yes. So if you look at this, right, if you look at the notebooks, right, for example, this is the feature selection right here, right? So what features are we selecting? And here, and that's why I kind of want you to go and get your own data set, because, to get this, you kind of need to understand the data set a little bit, right? For example, we know, right, race and sex plays an important role on your earning capacity, right? I mean, right, sadly. So you say, you know what, I'm going to start with these because I know these are important variables. Right? So yeah, so you need to kind of understand the data a little bit to do the feature selection and clean up and things like that. And again, there's no magic pill, guys. Just need to work on a few data sets to kind of develop a sense for it. That's it. And that's why I'm kind of really pushing you guys to pick your own data set, right? So let's say your field is biology, right? Let's say right biology, so then go and find some data along this field. Let's say your field is, I don't know, like civil engineering, right? Then go find some data set that's in your area of expertise, right? So then you understand the data. Because if I look at some biology data here, I have like no idea what it means, right? I mean, I don't even know, okay, is this a valid value? Should I clean this up, right? So to understand this, you need to understand the data. So that's why I recommend, whatever your field of study is that just go pick some data set in that field of study. Yeah, so. Good, guys, very good, very good. So I think we have in a pretty good group, right? Because again, the only thing I'm going to encourage you guys is like, please, right, complete the assignments, right? Because that's the only way you're going to sort of get the maximum value out of the class, right? So, and I know some of you have been very, very diligent about submitting assignments, so thank you. So keep it up. If you're a little behind, right? If you have work, whatever, right? Please, make some time, at least an hour a week, right? To kind of do the assignments. So, good, guys. That's it. Anything else? All right, close this. Oh, okay. Yep. So, guys, I understand. Things will happen. Work will work, right? Family, right? Things will happen. So, and that's why so sometimes people message me privately and say, "Hey, I'm a little behind." That's completely okay, right? So don't worry about this. Just try to catch up. Like for example, right? So let's say you missed last week. So you kind of missed logistical regression. That's okay, right? All you did was you missed one algorithm, right? So kind of keep up with us on SVM in the next few weeks, and then when you have some time, you can go back and catch up on logistic, right? So don't stress out. So you don't think like you had to kind of follow the path. It's flexible. Okay, so good, guys. What was the question? I want to make sure I didn't miss anything here. Yes, I will. Yeah, David, I see your question now. Yes, I will add these. So the way I would add this is basically I will put this in the guide, right? So this way it's not lost, and we will will have this. Yes, pipeline is in my pipeline. Yes, I will. It's in my to-do list. We will do a section on pipelines as well, right? So the idea here is we want to knock out the basic algorithms, then we sort of focus on the process, right? Okay, so now you all know all the algorithms. Okay, how do I pick the best algorithm? So that's going to be cross-validation, right? How do we kind of do the sequence of tasks repeatedly and without having to do a lot of manual work, pipelines, right? So those are kind of what I call sort of high-level concepts, and we will get to those. Absolutely, yeah. Good, guys, very good. So I think that's it. Unless there's any questions.
Between these classification algorithms that you mentioned here, which one is the most fastest one?
So actually, if you look at the competitions now, a lot of people use actually random forests, right? And also there's another one, XBoost, right? So these algorithms have been known to produce good results. So we are kind of building up, right? And the trees are the next section, right? So once you guys know the trees, like the random forest and XBoost trees, they are pretty popular. So if you look at the computation sites, a lot of people have been using these. All right, yeah. And we'll get to those, don't worry, yeah. All right, guys, that's it. We are done. See you guys next week. Keep an eye on the emails and the group and Slack for the next assignment, right? So, all right, guys, thank you so much.